So this is AS level chemistry 2.4 organic chemistry. So this is like the basics, the starting of the organic chemistry that we're going to do. So first things up is something called nomenclature, okay? And that's looking at different types of organic compounds and what kind of functional groups they have, okay? So alkanes are what we know as saturated hydrocarbons, so their functional group, which isn't really a functional group because you'll find in all of them, is the C bonded to a C. Now alkenes are what we would call unsaturated because they have at least one double bond, carbon-carbon double bond. Halogen are alkanes, a little bit like they suggest, they contain a halogen, normally chlorine or bromine or iodine. Alcohols, their functional group is OH, and you might hear that being called a hydroxy group. And carboxylic acids have got a double bond O and an OH. So they're all the kind of like different functional groups that you're going to need to know for the next couple of topics. So we say each of these organic compounds then, so anything that is an alkene belongs to something called a homologous series. Okay, so homologous series is organic compounds which have the same general formula, react in a very similar way, okay, and often differ by how many carbons are in their chain. So that means the boiling point increases because the higher the carbon chain, the increase in the boiling point, okay? Depending on homologous series, organic compounds will have different boiling temperatures and different solubilities. Solubility often depends on whether it's got hydrogen because of the hydrogen bonding. Okay, that's a stronger bond than the bond just between a carbon-carbon, so that would give it a higher boiling temperature. Okay, the stronger and permanent dipole attractions, the more hydrogen bonding there is, the more soluble an organic compound will be in water because it's attracted to the polar water molecules. That's just a bit of an overview of homologous series and what happens with their boiling points. Okay, something just really quickly to mention with boiling points is something called branching. So branching is when you've got isomers, so it might be one like that, and imagine I put all the hydrogens there, so that's a straight chain isomer, whereas a branched chain isomer would be more slotted together. Okay, so it's got a smaller surface area, so it's got the same number of carbons, but it's branched together. Okay, that branching means that it's got a lower boiling temperature because it's branched, they're closer together. Surface area contact is small, so lower the boiling temperature, because when it's spread out like this, the bonds are more spread out, so it's harder to break them. That's a smaller surface area, more like to be able to break them with heat. So moving on from there, we're going to go down here to naming organic compounds. Okay, so something that we would have done last year. Okay, you need to know the different starting for all the different elements, so meth, eth, prop, bute, pent, hex, normally up to 6. Okay, another thing that might be worth mentioning, which I'm going to add just back up here, okay, is that if it's an alkane, it's going to end in A and E. If it's an alkene, E N E. Halogens, because they're alkanes, they still end in A and E. Alcohols are O, and carboxylic acids are oic acids. Okay, so we count them out. So if we had 6, it'd be hexane. So we know the answer, hexene. That would still be hexane. That would be hexanol, and this would be hexanoic acid. Okay, so moving on, we're just going to have a look at naming one. Okay, these are kind of like the rules you need to remember to name them. Obviously, there'll be loads of different ones. First thing to kind of mention, if it's that way round, that's still fine. Okay, that's just the wrong, it's still a compound that you can measure. Okay, so first thing you need to do is work out where your longest chain is. Remember I said if it's that way, it's still fine. Okay, so with this one, we know it's going to be hex. So our prefix, our start, our star is going to be hex. Okay, we're then looking for a functional group. Okay, anything that says a functional group. Is it just carbons to carbons, which is fine? Got carbon-carbon double bond. What has it got? In this case, it's got an OH. Okay, because that's the most important one, because it gives us the name of what it is, we number them this way. Okay, because that's the most important functional group there. So it's on the second carbon. So we know that alcohols, or the OH group, stands for 2. So it's going to be hexan 2-ol. Okay, we've then got 2 other functional groups. We've got one there and we've got one there. So we've got two functional groups, okay? One's an ethyl, so that's C2H5, looks like a 3, 5, and then CH3. What we're then going to do is put them in alphabetical order. So ethyl would go first, so it's going to be 3-ethyl 5, because that's where it is, the third carbon, dash methyl, okay? If I was to replace this here with a chlorine, okay, it would then be 5-chloro, 3-ethyl hexane, 2-ol, okay, because chlorine is higher up in the alphabet, or Cl. If I then put another chlorine there, it would be 5-dichloro, okay, because there's 2 of them. You can have trichloro if there's 3 of them, okay, but that's the kind of thing we'll be looking at, okay. Then you might get asked to draw them, okay, so looking at their displayed formula. We're going to start off with empirical formula, okay. Empirical formula is something you would have done in year 10, normally using the mass numbers, or it might use percentages. So out of 100%, you might say, oh, it's got 70% aluminium, 30% oxygen, or whatever, but this one's using mass. You're then going to essentially do the mass over MR, or the mass number. So in this case, you are working out the number of moles. So in this case, it's just the mass numbers of them. So that would be 0.4 and 0.6. Okay, so you're using their mass and their mass numbers. You then divide by the smallest. Divide by the smallest, it gives you 1 and 1.5. You can't have 1.5, you can't have like oxygen 1.5, so you have to double it. Double it, okay? So doubling it would give you 3 and 2, so the compound would be Al2O3, okay? Molecular formula then, it might give you the MR, so it might say the MR is 140, work out the MR of that, divide it by 140, so say the MR of that is 70, I know it isn't, just for, so 2, that works out as 2, so it would actually be aluminium 4O6, okay? So the molecular formula is the true number of atoms, and often they give you the MR of it to work out the molecular mass, okay? General formula, so all members of the homologous series have the same general formula, that's the one for alkanes, okay? Alkenes is the other one that you most probably know, CnH2n. As we go along, you'll learn the rest. Structural formula, so showing the structural arrangement of atoms within a molecule. So how are they worked out? Structural and displayed. Displayed, so structure is just how they're arranged. Displayed, you have to show every single bond. So every single bond you have to show in displayed. So if they say structural, you can kind of just do it, make sure the carbons are bonded at the right place. Displayed is when you have to show every single bond. And skeletal, okay, it shows only the bonds with the functional groups, okay. Hydrogen is assumed to be bonded unless otherwise stated. So it'd be like 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So each has an end, okay. So it's removing it all and you bend them, okay. So that's kind of like the basics of organic chemistry. We're now going to move on and kind of look at isomers. There's 2 types of isomers you need to know. You obviously need to know the definition of an isomer. So an isomer is a molecule with the same molecular formula but a different structural, spatial arrangement of atoms. The variation can lead to different physical or chemical properties. Okay, so nice basic ones now. Looking at the chain. So chain is just branching them off. Nice and easy. That's mostly the most common and easy isomer you'll come across, okay? So they're arranged differently, gives a branch chain. The name of the molecule changes to reflect this, but the molecular formula is still the same, okay? Position isomer, again, a nice common and easy isomer. You're just moving the functional group. So it remains the same, but the position of it changes, okay? Name will change to reflect its new position. And then the final one of a structural isomer is a functional group. So it's a little bit complicated. Also referred to as a functional group isomer. These isomers have the same molecular formula, but atoms are arranged to give a different functional group. So these here is cyclohexane, so it's kind of created like a cyclic formula. Okay, the name of the molecule changes to reflect the new functional group. So you notice they've actually got different functional groups. That one's got double bond. This is a cyclic one. But if you were to count the carbons and the hydrogens, it would be exactly the same. Okay, so they're structural isomers. Then you've got stereo isomers. Okay, so they're isomers that only exist with something that has a double bond. So they only exist if something has a double bond because the bond is restricted to rotation. Okay, commonly exhibited by alkenes, the presence of two substitutes on both carbon bonds at either end. So you can only exist if you've got different things, and it's got to be on either side. So this is one side and this is the other side. Okay, what you then do on both sides is give them priority numbers based on their mass number. Chlorine's got a bigger mass number, so that would give priority 1, and on this side as well, priority 1. Okay, same thing, split it in half, priority 1, priority 1. So these two are opposite each other, so we call it an E isomer. These two are on the same side, okay, and we call that a Z isomer. Okay, so all you do is they've got the same name, they've just either got E or Z in front of them. The reason for that is they're double bonds. Okay, and then finally looking at different species that you might come across. So free radicals are a species that contain an unpaired electron, so a set of unpaired electrons, and they're often displayed like this. What they want to do is bond with something to or react with something to gain another electron and form a pair. So it's an unpaired electron. So electron on its own, unpaired. So electrophiles are electron deficient species, though they love electrons and they want to accept a pair of lone electrons. So what often happens is you've got something like this, hydrogen bromide. It's essentially got two because it's covalently bonded. What happens is a homolytic fission, and it creates a dipole where both the electrons move this way, making that negative because it's got more electrons, and this then becomes positive. It hasn't got any electrons, so it hence becomes an electrophile, often attracted to double bonds because they're electron rich areas. It wants to gain an electron. And then nucleophiles in the opposite direction, then a species that already has a lone pair of electrons. So in this case it has two, so it has a pair of lone electrons and can be donated to an area where it's electron deficient, so often a positive area, normally involving hydrogens and alkanes.